Hey guys, welcome to our study of work, energy, and momentum, and it's kind of piggybacking on some of the stuff we ended up with, like our inclined plane. But we'll kind of jump into it here. Work is defined as the transfer of energy from one body to another, or a better way to say that would be work is the change in energy. And how we say that, grab my pen here, but work is equal to the change in energy of the object. And remember, we defined the change in energy as the final minus the initial energy. When we do work, we plug energy into the system. Okay, so we have a couple of equations we can use. Work is force times distance. And the units of work are joules or Newton meters. And so remember, the force is in newtons, the distance is in meters. So this is a Newton meter or a joule. So that's what the work is. Work is energy. You'll see later on, if you know what torque is. A torque is a Newton meter. They're very different, but we'll discuss that in a little more detail later. So let's take a look at our first example here. So when you pick something up, you're basically working against gravity. And so the first thing you do is we draw the free body diagram, and we know that there's a force picking it up and the force of gravity pointing down. In this case, because it's at a constant velocity, we know the net force on the object is 0. So down here at the bottom, I'll kind of start working on this. I know that the applied force, F, is equal to the Fg of the object, which means work is Fgd, that's what I'm going to have to do to apply it, is equal to mgd, that is the substitution. And I start plugging everything in. Work is 2 kilograms. That's the mass of the object. 9.8 is the gravity. And then I'm moving it 1.5 meters up. So it looks like the work is about 29.4 joules of energy on the object. Once again, because the velocity is constant, we know the net force is 0. So that's not too bad. Our second example over here is how much work is done on a 4 kilogram medicine ball that is held at a height of 1.8 meters for 10 seconds. So this is a pretty typical question. Is energy being used to hold it up? Well, of course, the answer is yes, I'm holding it up. But no work is being done. Here's why. Remember, work is the force times the distance. Well, the force that I have to hold the ball up is equal to its weight. So I have Fg times d, so mass times gravity, that's the force of gravity. But I'm not moving the ball up or down at all. So if my distance value is 0 here, that's how I get 0 joules of work if I'm holding it at a height, basically holding it still for that amount of time. So I'm spending like physiological energy, biological energy, your muscles are being used, but I'm not doing any quote unquote physics work. I'm not holding it up or down, and we'll do a little quick demo in class when we come in. Okay, on to the next one. This problem is a bit more typical of the questions that we'll see. We have forces acting on an object at different angles, and so we got pretty good at doing that. So one of the main things that we're going to have to do is we're going to have to draw the free body diagram. So I know there is Fg pointing down. There is the normal force pointing up. Here there is friction acting on the object. And I have the force of the dude pulling at an angle, and then I have the angle here that it's applied at. I have both the x component and the y component. So remembering our sine and cosine rules, our trig rules, Fy is F sine theta, Fx is F cosine theta, so we've broken that apart. The question is, does the vertical component do any work? And the answer is no. Reason for that is Fy is perpendicular to the direction of motion. So the quick rule is when finding the work done on the object, we only consider the component of force in the direction of motion, or we'll say parallel to the direction of motion. And that's going to make sure we get the correct component. So to finish off our question, how much work does he do? What we have to use is we're going just his applied force. So work for him is going to be F in the x direction times distance. So for him, work is going to be the F cosine theta. So for him, it'll be 35 cosine 40. The distance the object traveled was about 20 meters. So he got about 536 joules worth of work done by pulling that object. All right. So here we have another same type of question. We have a biology student pushing a rope 15 meters across a flat surface. The student pushes with the force of 220 newtons, while there's friction involved on this. So there's adding a bit of a wrinkle to our question here. So here's our object. We have the applied force pointing this way. Let's say force of friction doing that. We have the normal force and the force of gravity, but the question kind of whittles things away for us. So basically what we're doing is we have to use the applied force, right? How much work is the actual student doing? So work is going to be the force times distance. So in this case, it's going to be 220 times 15. And we get about 330 or 3,300 joules worth of energy done by the student. Now, the other question you can ask is, what is the work done by friction? Well, you do basically the same thing. Work is the force of friction times its distance. Here we have 120 newtons of friction force, and we have that 15-meter distance. So here we get about 1,800 joules done by friction. And so we'll talk a little bit more about this, but basically friction takes energy away from the system. It slows things down. It wants to stop it. Remember, it opposes motion. So that's something to be remember about. I remember when using total work done, we always use the applied force of the object. So when we're talking about the person or whatever, work done by, right? So let's just say work done by, and that'll help us to understand which one we're using. To scalar or not to scalar, that's always a big question. Work is a scalar, or energy is a scalar thing. I can't have quote unquote negative energy, but I can have energy taken away from the system, and that's something we'll talk a lot about. But when you have these cars or objects moving, if you're having something accelerate from rest, there's positive energy into the system. There's a net positive energy. When you're stopping something, you're taking energy away. You're making it slow down. Lifting something above your head, you're giving it energy. You're pushing it up. And once again, a ball rolling down a ramp, it's actually gaining energy by speeding up. So when talking about speeding up and slowing down in energy, we have two types of energy. And I know we've discussed this before, especially in middle school perhaps. But we have potential energy and kinetic energy. Potential energy we call stored energy. the potential to do something. So here's stored energy. We have E sub P equals mgh. That's typically what we use. I like saying PE generally, it's just easier to write sometimes. The big note on this is it's relative to a reference point. So that reference point, I can have a quote unquote positive or negative energy depending on what's going on. And then over here I have kinetic energy, which is the energy of motion. And I like using kinetic energy as 1/2 mv squared. Once again, quantities I think we remember, so we're not going to spend too much time talking about that, but more how to apply them. So work done on an object, this is a really important idea right here, the work energy theorem for net force. The work done on an object is equal to the change in kinetic energy. Work is equal to the change in kinetic energy of the object or the system. So here I have a car accelerating from a certain speed to another speed. Over a distance, determine the average net force that was required to do this. The reason we use net force is sometimes things change, the fuel changes, all that stuff. We like to use the average net force over that time. So if we look at this and say work is a change in kinetic energy. So breaking this down, I know that there is a final kinetic energy and an initial kinetic energy. And I know that there is a force times distance, and it's equal to all of this kinetic energy final minus initial. I can start plugging stuff in. I know my force, or I can break this down one more time actually. Here I can factor a little bit. I can have VF squared minus V naught squared over, oops, this should be distance here, and my force should be over here. Don't make that mistake. And there's this solved symbolically, right? This is the amount of net force required to have an object speed up or slow down, depending on which way it's going. And here we'll just plug everything in. There's everything plugged in, and when you crunch numbers, we should get an average force of 3386.67, so about 3387 newtons of force. Here I got a positive sign, that's important. My object sped up and it didn't slow down, so that's going to be important to recognize also. Here we're going to start graphing things a little bit more again. Here we have a graph of the force of an object versus its displacement. And one of the things to remember or to know that the area of a force distance graph is work. So the area of a force distance graph is work, or force versus distance. So here we can determine the total amount of work done, and one of the easiest things to do is we can break apart this into different areas. And I have a triangle, two triangles and a square. So we'll call this area 1. So area 1 is 1/2 base times height. So all I'm doing is plugging in the values. The base is 2, the height is 20. So I get it, the first area is about 20 joules. I'll use the second one here as green. So the second is base times height. The base is 4, the height is 20. So I get the area of the second one as about 80 joules. And then I'll use this third one here. This third area is 1/2 base times height. The base is 4, the height is 20. And so the area of this guy is about 40 joules. So the total amount of work done, add all that up together, we get about 140 joules worth of work done for this particular situation. The final speed of the object, we can assume negligible friction, so we're assuming no friction. Remember, this object was initially at rest, So we can use the work energy theorem by say work is the change in kinetic energy. If I know my kinetic energy at the beginning was 0, that means my work is basically the final kinetic energy of the system. So work is 1/2 mv squared. So when I plug in my numbers, I get 140 equals 1/2. My mass is 15 v squared. Solve that for v, I get about 4.32 meters per second as the final speed of my object. So there's lots of different things we can determine based on our graphs that we can use. So a quick summary of everything we've looked at right now. We have work is the change in energy of the system. It is also the force times distance of the system. I know that the change in kinetic energy is equal to work, and it's the net force times distance. And then the law of conservation of energy. Once again, I think we've heard all of this before, but it's nice to get a quick refresher. Energy cannot be created or destroyed, only changed from one form to another. Therefore, if only conservative forces act on the system, we'll talk a little bit about what that means. The total change in energy is always going to be 0. That's actually really interesting. Total energy, so basically all the energy at the beginning is equal to all the energy at the end. That means the initial kinetic energy and the initial potential energy has to equal the final kinetic energy and the final potential energy. Another way to write that is the total kinetic energy change plus the total potential energy change is 0. So two different ways to say the same thing. One of the best ways to see that is the prototypical roller coaster question. We have a roller coaster that has a couple of change in heights. And so when we sketch this out, we have a high hill and a low hill. And what we do is we know what the heights of these hills are. This first one is 55 meters, and the second one is 30 meters. And the distance between the two is 25 meters. And so using this, you can figure out how much energy each point has based on where they are. So we can do it this way: the initial kinetic energy of the system plus the initial potential energy of the system equals the final kinetic energy of the system plus the final potential energy of the system. So what I'm doing is I'm using this as my arbitrary 0 point. And once again, this is where that potential energy thing came in. So the change in heights of the two objects is only 25 meters. The other thing I can do is I can look at my initial energies and say, initially there's no kinetic energy, and at the end there's no potential energy. So the only thing I have to work with is my initial potential energy at mgh is equal to my final kinetic energy at 1/2 mv squared. Notice my masses cancel on this. And I get gh equals v squared over 2. Looking for the velocity, throw some algebra at it, and I get 2gh, the square root of that guy. When I crunch the number, I should get about 22.1 meters per second at that point over here. We can call this point A, point B. So the velocity at point B would be about 22.1. So this little method right here is going to be really helpful in solving these conservation of energy questions. Last topic we'll talk about is this idea of a non-conservative force. So basically anything that takes something away, like friction, that's a non-conservative force. In other words, I can't account for it at the end without changing a couple of things. The work done by friction produces another form of energy we know as heat. Without friction, we wouldn't walk, but friction does a lot of damage to moving parts, moving things. This heat energy is quickly converted, maybe we should have said converted here, that's weird, converted, or radiated in all directions and is effectively dispersed. Consider a block of wood sliding down with a small amount of friction, so basically what we've done in class a few times. How would the block's kinetic energy at the bottom compare to its kinetic? Well, remember, we've talked a lot about that. Here we have point A, and down here we'll have point B. So the potential energy at the top would be greater than the kinetic energy at the bottom. I wanted to use red there. Right? Some of that energy is lost due to friction. So if they're not equal, you can assume that something went away. We know that the total energy in the system, it has to remain constant, right? As the law of conservation says it is. So we can rewrite this just a little bit as the initial potential energy plus the initial kinetic energy of the system is going to equal the final kinetic energy of the system plus the final potential of the system plus any energy due to heat. And so this is where sometimes the discrepancy happens. Once again, the other way to write that is the change in kinetic energy plus the change in potential energy plus the change in the heat energy or anything lost. That still has to equal to 0. So how do you do a problem that has that friction idea and we play with the energy in it? Well, here's how you start it off. We have an object is pushed down a ramp with initial velocity of 6 meters. So up at the top, it already has 6 meters per second worth of speed. And then at the bottom, it has 7.5 meters worth of speed. And we're figuring out how much thermal energy is due to friction. Well, the easiest thing to do is figure out how much energy is at the beginning of the system. So we'll call this point A up here. Over at point A, we'll kind of work on it this way. I have an initial potential energy of mgh, and that is 5, 9.8, and 1.5. Looks like I get about 73.5 joules worth of potential energy. I also have an initial kinetic energy, that is 1/2 mv squared. So I have 1/2, let's see, my mass is 5. My velocity at the beginning is 6. So here I get about 90 joules worth of energy at the beginning. Down here at the bottom, at point B, I have a final kinetic energy of 1/2 mv squared. So that's 1/2, 5, and 7.5. That gives me about 140.6 joules worth of energy. And so when I take a look at that, at the start, I have about 163.5 joules. At the end, I have about 140.6 joules. So that means I had a loss of 22.9 joules worth of energy due to friction. So that's how you could determine how much energy is lost due to friction. And then part B would be to determine the force of friction. So once again, you can do all of this just by working on the friction. We know, it's actually pretty quick, work is force times distance. The work, remember, was the change in friction. So over here, that was the total loss or the total change in energy. That part was generated by friction. So that's my work value. That's 22.9. Force is what I'm looking for. it slid down that distance of 3.5 meters. So it looks like I had a friction force of 6.5 newtons. So using this energy idea way simplifies how I can look at these dynamic questions, because remember, we had to do Fg this way, normal force. I had components pointing this way, components pointing this way, and then friction going here. It adds a different way to be able to solve some of these questions, which is very exciting. Anyway, thanks for watching. We'll have a couple of summary questions I'll have you guys for when you come into class. And thanks for watching. Talk to you later. Bye.